bucket. Measure the height that we're standing at from this room. So we have tape measure that's long enough. So we're just gonna use this string, and Charles over here is gonna help us do that. We made a mark on a string where the banana landed, and I just coiled it around my arms. So there's 4 circles, so I just folded it in half. So 8 times this length, which is...
It's approximately 34 centimeters.
34 centimeters, so 8 times 34 centimeters is the height of this building where we're standing from.
Okay, hey guys, so here we have our slingshot that we'll be using for our experiment. So right now we want to find out its spring constant, so we want to find out the change in length without any mass, and with the mass of 300 grams, which are like 100 grams each for like 3 oranges. But so right now we have a length of 8 centimeters. We're just going to find the change in length, so we're not going to bother measuring the whole thing. So when I put these oranges, the length of the spring goes to 15 centimeters, which means there's a change in length of 7 centimeters.
Alright, so a spring constant is found using the relationship between the extension of a spring and the force applied to cause that extension. So there's an initial, the natural spring length was 8 centimeters, and it extended to 15 centimeters. So that means our extension is a total of 7 centimeters. And the mass that we used was 300 grams, and the force of 300 grams is Fg equals mg, so that's 0.3 kilograms times 9.8 newtons per kilogram, which gives us 2.94 newtons. Now, once again, our K constant is in newtons per meter, so if we divide the force that it took to stretch the spring, and we divide it by how much it stretched, we could find our K constant. So our K constant equals our 2.94 newtons divided by how much it extended, caused by 2.94 newtons, which is 7 centimeters, or 0.07 meters, and that equals 42 newtons per meter, and that is our K constant.
Okay, so first off, we're finding the velocity of the orange. So the orange is shot on only a horizontal component, so from this we only incorporate x directional components. So we've concluded, we've measured that the garbage can is 8.9 meters away from the window, so that's the horizontal displacement. And then we divide that by the time that we found from an initial shot, and that was 1.51 seconds. So due to this, we found that the velocity is 5.9 meters per second. And we found that the energies present is the elastic energy is equal to the kinetic energy. So from this, we can cancel out the halves, and there is just spring constant times the amount pulled back squared is equal to the mass times the velocity squared. So rearranging this equation to get the x value, we conclude that we have to pull back the catapult mechanism 0.29 meters for the orange to go from here into the garbage can.
Okay, ready, boys? Aye. Alright, so we made our shot, and some source of error that may have caused our missed shots are one, the clementines weren't exactly 100 grams, like each one wasn't exactly 100 grams, which may have caused changes in our K value. Secondly, this elastic is not 100% efficient, which means that when we did our calculation with EG equaling EK, there's actually a conversion factor of efficiency that we didn't address. So those are 2 main factors that would influence our results.
Hey, and you guys yelled really loud and you broke my mic, so like...
Well, we made the shots, yeah.
Gotta
Shelly
celebrate.
hard, boys, Shelly hard, baby!
Celebration!
Yay!